So as I said, it's basically showing this. So first taking a bottle, put it on. You're going to let air into the Niskin to replace the water that's coming out. So you open the top valve, you open the bottom valve, let it out slowly. This is a clean bottle. It's not being rinsed ahead of time. The idea is to fill it up with the minimum amount of splashing and therefore gas exchange. And that takes time and trouble. One easy way to do it is to count while filling the bottle, and you'll see it takes a certain number of seconds to fill. And so if you want twice as much water to go through, you count for twice as many seconds. He went 1001, 1002, and then he went 2001, 2000, until he went back to 2012. After it's all, this is essentially flushing water through the bottle. So the ideal is to leave the water in the bottle with exactly the level of CO2 you'd want. Now, he's very carefully removed that off and taken it away. But there are different ways of getting what we're going to do next. Now, ultimately, you're going to want room in that bottle to put the stopper in. He didn't have it there. You'll see that later. Another approach that Chris will show you later is you can use the fact that the tube itself takes up a volume of water. And if you stop the flow and pull the tube out, then necessarily there's less water in the bottle. And so both possibilities exist. We walk over, we have an area, it's set up to do this. We've got the bottle, a cap that's ready greased, and everything there. So the variety of things that we're using, essentially the bottle, the gloves, a way of dispensing the mercuric chloride. We're putting into this bottle about 120 microliters, and we grease the stopper with Apiazon L grease. Here you can see greasing the stopper. Basically, what we do is 4 parallel lines. Why? Because when you push it into the bottle, air can come out along the sides right until the last moment. So full bottle, too full a bottle. You need about a 1% head space, and you'll see the level this comes down to. It's just being pulled out with a syringe. We know that it takes about 25 mils to get all the water we want out with the stopper as well. That's about the level that we fill these bottles to. Mercuric chloride. Now, we're using one of these auto pipettes. If you're doing hundreds of these bottles, there are better and easier dispensers to just put in a volume. This is convenient for doing a couple of samples. Stick, take the stopper, sure, just by twisting the stopper a little bit. Here we're going to stick a rubber band over the top of the bottle, and this is the style we use, which has that clip. It clips around the neck of the bottle. Those bands are impossible to squeeze both of them together without a drill press to do it. So we loosen one off and clip it on.
Rubber banding with a different type of rubber band.
Yeah. So very straightforwardly, you're going to have a clean bottle. If the bottle's not clean and you're going to use it again very quickly, probably just rinsing it first with some of that seawater is fine. But if you want a good sample that you're going to then ship to somebody else to analyze weeks later, you really want a sparkling clean bottle to begin with. The headspace is about 1% of the headspace. You've got to allow some room, because if there is a change in temperature and the water expands, you do not want the stopper pushed out of the bottle. So it has to have some gas space there. But if you've got gas space there, then the gases that are dissolved in the water and the gases in the headspace will ultimately equilibrate. If there was a different composition, you'll change the water composition. 1% is an effective trade-off that changes in the water composition over pretty well the full range of seawater compositions for CO2 levels would not be noticed. The bottle itself these are made of a Pyrex type of glass. In our lab's experience, any other glass apart from a Pyrex type of composition, the alkalinity of the sample will change with time. If it's another fairly high quality glass, slowly, a few micromoles per month. If it's a cheap glass, quickly, a few micromoles per day. But they change, they always change. The glass top, the gas, the grease ensures a long-term gas-tight seal so that the bottle really does stay with what you put in because you killed stuff that was in there by putting that mercuric chloride in. The amount that's chosen there is about 0.02% by volume. So we had almost a 600 mil total. It's actually about 560 when it's filled up to the top. So hence that was 120 microliters. If you've got a smaller bottle, you'd need less mercury. A larger bottle, you'll need more mercury. Once something's in a bottle like that, how long does it keep? The answer, I think, is realistically we don't know. Our reference materials that were alluded to this morning, which are natural seawater from off California that we do filter, and then we add mercuric chloride and put it in bottles. We have no evidence that the alkalinity is changing over 10 years. As far as we can tell, we get the same numbers 10 years later. As far as we can tell, it's within 2. For total carbon, certainly it's not changing significantly over 2 to 3 years. So once it's in a bottle like this, it can last for years. Now, you can cut corners. You can have a lousy bottle, a crude cap, and analyze it that hour, and you're okay. Unfortunately, most of the equipment we have is not so reliable that it'll be there for you to analyze immediately. You take the sample working the way it was this morning when you tested it before you went to take the sample. So I advise taking the samples carefully as though you had to store them for a long time. And if you don't, great. Anything?
You want to say a few words about how you clean the bottles?
We clean the bottles in my laboratory. These reference materials has gotten to big business. Well, last year we sent out about 6,500 bottles of reference material, and we clean all the bottles first, and we get back the old ones and reuse them. So we clean them. If you have a bottle that's had seawater in it, that's got a label, we rinse it. Well, we empty that out. That's a mercuric chloride containing seawater if it's one of our samples to be collected. We rinse it just to get a little bit of salt away. Then it goes into a high temperature glass blower's oven that burns off the grease and burns off the label. This leaves a sort of slight powdery dust in there. It then goes into a dishwasher that's plumbed to deionized water that scorches it with hot, clean water, and then we just leave it in a laminar flow bench to dry, and then we put some kind of cap on it to keep the bigger bits of dirt out. But you can't keep everything out, which is why we like to poison the sample going in the bottle, because the bottle itself may have something that could contaminate the sample. So to get it that clean, the high temperature is actually a very effective way of cleaning the bottles. It burns off any organic material, including bits that were living. It's about 560 degrees centigrade. It's just below the annealing temperature for the glass itself.
We do 500 for 4 hours. It's at temperature for 4 hours. It takes 4 hours to cool it down after that.
And so, you know, that might be overkill for washing. Frankly, it's a difficult experiment to design how you start cutting corners without doing it. At this rate, we can wash about 60 bottles a day in 3 hours of work regularly, over and over. So 5 days, 300 bottles get washed, and it works for us. Yeah?
Photo samplers that they have out there now are all fitted in bags, not throwing some big bottles. Do we have any understanding yet as to what we might recommend for a bag sample, and how long we might be able to keep that before we have to clean one?
We've done a small amount of work with bags, and bags have one clear and obvious advantage, which is that there's no need to worry about a headspace because you don't have a headspace. The flexibility of the bag copes with that. Thus, also you can take, when you take a sample, the headspace doesn't get bigger, the bag gets smaller, so the opportunity for gas exchange is very small. Bags potentially work well, but at the moment, the material we believe is likely to be best is trilaminate. Trilaminate is essentially a polyethylene on either side of an aluminum foil. And the reason there is to minimize any gas exchange. That metal barrier in the center stops gases going through. Unfortunately, we've not yet found a completely reliable source for connectors onto the bags that don't leak around the connector in a proportion of the bags. And so the bags we've had that work well clearly have worked for a number of months. That's as far as we've tested. But the connector has leaked on too high a proportion of those bags of the ones we've dealt with. Sooner or later, I'm going to have to bite the bullet and say, I'd like to try your bag. I understand the minimum order is 5,000 bags. But at the moment, we're working with smaller minimum orders where they're pretty well hand assembled, and it's not working as well as I'd hope.
We've had a similar experience. We've done 3 batches of bags. The first ones were fine. The second one, we found that the alkalinity was changing, was decreasing by 5 micromoles a day. The alkalinity,
Yo.
the DIC was not changing, but the alkalinity was decreasing by 5 micromoles a day.
So it's actually reacting with the bag?
I don't know what was happening. We've never figured out exactly. The third batch seems fine. So now what we do is every time we get a new batch of bags, we fill them up with CRMs and analyze them over a couple of weeks to make sure that they're, I mean, we think
That they're not changing drastically.
Yeah, I don't know what it is that caused that problem with that one batch.
So are you routinely using bags, Chris?
Like I say, we've done three sets of experiments
This
now.
is just experimental, not routine. And Chris, that's from the same manufacturer every time?
Yep, which actually is an older gentleman that makes the bags himself, and he's having lots of health problems, and he's a crotchety old man that really doesn't like to talk to you, and so we've had trouble getting any information about what he might have done differently this time compared to last time.
Are those bags supposed to be sterile?
They're supposed to be.
Are you absolutely sure it can't be maybe some of the analytical protocols after, I mean, maybe
Oh,
that
no.
one analysis, you're absolutely sure that it was the bag and wasn't?
Yes, because we were analyzing reference materials and bottle samples, and we even had some bags left over from the first analysis that we analyzed again that were 6 months old, and they came out exactly right on, and the others, every day we analyzed them, were changing.
I had a similar problem with these biomedical bags, which are made to reduce it for sampling blood, and they have pretty high specifications that don't allow CO2 to exchange across the blood. And we had similar problems, Chris Langdon and I did some work with them. Some of the bags seemed to work well, and then some of them just were extremely off to where it couldn't have been operator error or something.
Yeah.
But the other problem is reusability. I mean, they're not cheap either.
Right.
You can't sterilize them. They have to be made for immediate, use only, and that defies the whole reason to have these auto samplers.
Right, yeah, we've never reused the bags.
Plus, it is awkward to imagine a system, though potentially capable, that will allow you to add the mercuric chloride to the seawater that you are putting into the bag.
Well, so we,
It can be done. That's one of the reasons I suspect they were testing with reference materials. It was there already.
well, so what we normally do is we spike the bags with mercuric chloride solution before we deploy them. The other issue you've got with the auto samplers, at least with our McLean sampler, is there's a fair bit of tubing from the pump to the bag, and there's no way to flush that. So you can either, what we ended up doing was refilling those tubes with DI water
Well, this comes to the kinds of things that Chris was referring to this morning, that essentially samples that have the ability for gain or loss of gas by exchange with the ambient air probably should be taken first, because as that, what you don't see when we do it in a Niskin as opposed to a clear bottle is, of course, as you're doing that, water is flowing down in the bottle and the headspace is replacing in the bottle. But worse than that, the sun is shining on the walls of the bottle, and so you actually have convective cells of water inside the bottle that are making sure that all the water has a chance to exchange sooner than you might have hoped. And as a result, the gas, what you really want is a trade-off between the ones that are going to be the most sensitive for the gas in theory versus what you can actually measure it. And as CO2 measurements are becoming better and better, I think we make a case that CO2 ones for things like pH or PCO2 or even total carbon ought to be pushed further up the traditional order of taking multiple samples from a single bottle. That's still a difficult sell.